Hey guys, my name is Mark Schvetz and I'm a developer at Chariot Solutions. We're going to start off strong with two excellent speakers, James Ward and Josh Suereth. Are both fantastic, and they're going to talk about, this talk is going to be a surefire win. I actually had the pleasure of listening to Josh a number of years ago. He was using Scala clandestinely at Google, and it seems like he's still doing it kind of clandestinely. So if you guys have a question, just like the keynote, put them into the Slack channel room A. And the audience could also upvote questions by reacting to them, and we'll ask questions at the end of the presentation. And just want to let everybody know that this webinar will self-destruct at 11 o'clock sharp. So here's James and Josh.
Awesome. Thanks, Mark. Thanks for having us. All right, let's switch that over. Is that showing? Okay. All right, so this is the evolution of object-oriented programming. I am James Ward. I'm a developer advocate at Google Cloud.
And I am Josh Suereth. I am a staff engineer at Google.
Okay, so let's start out with a little bit of a history of object-oriented programming. So we have gone through a cycle of learnings a number of times with all programming, but today's talk is on object-oriented programming. And what we see happening is that we use a technology, in this case object-oriented programming, and then we find some limitations with the paradigm that we're in. So an example from my background of Java is I used Java EE or J2EE back in the day, and there were some limitations that cropped up in that approach to doing things. And so then we developed some patterns to work around those limitations. In the case of Spring, we started with XML dependency injection as a better way to do things than Java EE for some people maybe not. But then those patterns turned into a new way of doing things. And usually this ultimately manifests in terms of language support for a new paradigm. And so annotations are the way that the Java ecosystem moved for doing dependency injection. And so we see the cycle happening over and over and over again in lots of different areas. And so what we're going to walk you through today is how this cycle applies to some new things that are changing, some new limitations that we're discovering, some new patterns that we're developing, and then some new language features that help move us forward.
Yeah, so today, right now, we have a gap between like our traditional OO design and like what you're doing for modern service-oriented architecture. Sorry, my neighbor is mowing. I apologize if that's
of course, the neighbor would be mowing the lawn right when we're doing a talk.
Yeah, what a great timing. Okay, so so previous architecture examples, you know, I grew up with star schema databases, 3-layer architecture, web business data, and a whole bunch of gang of 4 patterns, right? And so when we started off with kind of like object-oriented on a single machine, where when we wanted to reuse and compose things, we were using like DLLs and shared objects of like C++ things, and it was really hard and kind of gross. We had some 2-tier architectures back then where we'd run a database and an application on the same system. Then we started moving to this multi-machine with these 3-layer architectures, started seeing things like Corba and DCOM and Java EE as like, let's throw some OO at the network, right? And treat the network as an object and try to have object-oriented communication there. And it kind of worked, kind of didn't. Like there were good bits and bad bits. And we moved on to this thing with REST, where we have a service-oriented architecture. We have an object with exactly 4 verbs, you know, get, post, put, delete. And that starts to make things a little easier to deal with, right? It's that abstraction kind of helped out a bit. And now we're on to microservices, where it's a very service-oriented architecture where we kind of try to make a service of like 1 verb. It's not always 1 verb, but you know, for the most part, you have a HTTP service that you call, and you give it a request and you get a response, you know, and you're talking about these like verbs that we're exposing on the network and kind of communicating between them now. And so that's kind of how things have been moving. And because we've kind of shifted this far with our network topology and how we do networking code, it's actually impacted how we write OO code in our day-to-day, you know, business logic.
So ultimately what we want is we want to reduce the code that we have to write, and we can do this through composition and reuse. And that's always a good goal. We want to write less code because that means less bugs and less work. We want to use higher level of abstractions to reduce the code that we have to write. We want to use more generic programming. That's just another form of reuse. But as we do that, we don't want to sacrifice performance, and we certainly want to be able to take advantage of multiple cores and all that kind of good stuff too. So those are the things that we want, and we want those in the context of this new microservice-oriented world, but there's some challenges. Polyglot is here, so we can't just apply our OO patterns necessarily because we have systems that are made up of all sorts of different programming languages, and they all have to talk together because we're in that service-oriented world. Our complexity of what we actually are trying to accomplish is increased a lot. And we can't just rely on inheritance and message passing, the traditional OO paradigms anymore. We need new patterns. We need new ways to think about how we put together systems. And so what we want to walk through is some of these new patterns and ways of doing things in the object-oriented world. So we're going to start with our first way that things are changing, which is going to be around mutation. So I've got a fun game that that I'm going to play where I've got a program, and this program has a function add1, and we're going to pass in the same value to this function a bunch of times, and we're going to just debug this program so we can play a little game to see what happens. Okay, so I've got my function. It takes a 2, and it's called add1, so we can kind of infer what we think it might do. So Josh, what do you think this is going to do the first time I run this?
I think it should actually return an integer value of 3. I would
Okay.
guess. Just by the name.
You are correct. You are correct. We gave it 2 and it returned 3. Okay, what do you think it's going to return if we do the same thing again?
I mean, it should do the same thing, right?
It should, but you know, there's got to be a twist. So we're going to return 4 instead. So we added 1 to 2 and it returned 4. That's weird. Okay, let's do it again. Oh, and this time we didn't even return an integer. We returned null. That's
man, that's why you had big integers there. Now I can understand.
And then, of course, calling it the 4th time there through an exception. Okay, so let's take a look at what that implementation did. So you'll see that I have a mutable value here, current, and I am doing some sneaky logic that is just mutating that current value every time we run this. So we've got this external mutable state for this function, and it's giving us kind of unexpected results. That's unfortunate. Okay, let's try this again, but I'm going to use that same add1 function, but I'm providing the first value here just as a static final integer 3. Okay, so let's try this. Let's try this one. Let's go debug it. And let's call that add1 function on our static 3. Okay, now what do you think it's going to return this time?
I mean, it should be returning 4, right?
It should, but nope, it's not. Actually, if we run this thing, which is going to take just a second to run, you'll see why in a second. Oh, it actually returned a random integer and another random integer. And
isn't this the same function you called before?
The same function, function. Yeah, isn't that weird? Well, if we look at this thing, what's actually happening is that we're doing some bytecode modification in this class where we got our 3 from. And that bytecode modification is giving us our random integer. So this is not too different from the world of Spring or Hibernate, where you've got some bytecode modification or something happening underneath the covers that is changing the behavior of your functions. Okay, one more example of this where we have very explicitly a function that takes an integer and adds 1 to it and returns it. In this case, we're going to give it 4. And if we go run this one, then this one is going to work as expected. We're going to get 5 every single time we call that thing. So that's great. Our function is working in a way that we expected it to. And so what we're illustrating here is what you've seen is mutability and immutability. So let's, why do we have mutability, Josh?
Well, so a lot of us, when we learned programming, we learned von Neumann architecture, which teaches you, there is you have memory and you kind of write to it and read from it, and that's how computers work. And generally, it's a convenient model, and it can be efficient for single-threaded CPUs, right? But we do need to mutate here and there. Like, that's kind of how computers function. But it has a lot of limitations for us. One of the things you saw was if I have a method that I think by reading it shouldn't be mutating state, but does, it can be really complicated to figure it out. I mean, no one's going to take an add one method and do something crazy, but they might update a cache when you call like a get method, and that can lead to crazy immutable results. It can lead to issues with composition. If I make use of this over here, and I violated some of the concepts of the mutation that I had, I suddenly can't make use of it over there because the composability isn't right. Concurrency is an issue. If I try to make use of a value that mutates state in 2 threads, all of a sudden my life just got really complicated, really, really complicated, real fast.
Indeterminate issues,
Yeah.
indeterminate state.
So equality is a fun issue. When I think of equality, I think of equality in hash codes, and I think of hash maps, one of my most frequently used collections ever. You throw stuff in a map, you kind of like look it up very efficiently, you kind of, disambiguate which ones they are, but if you start mutating stuff, your hash code changes, your equality is broken, and you can no longer find it in that map. It becomes an issue, right? The same object is no longer the same thing, and you have referential equality and you have deep equality, and they're different things, and oh my gosh, what's going on? I have a little story about refactoring some Hibernate code where we had an old, this is EJB3, I believe, database or system that was talking to a database, and for the most part, the system was reading some code, doing some transformations and writing out some objects, right? And Hibernate's very good at that. It kind of takes away the database layer so you don't have to really think about it. But we also had 2 other use cases. One was we're doing crazy analytics where we had to really control the SQL that we wrote and do a very efficient database read. And the other thing we had was we had to actually send some messages at the end of transactions. And we had to do it based on whether the transaction succeeded or failed, and we had to kind of have an undo operation if the transaction failed to kind of recover. That was actually rather hard to do in Hibernate because of all the weird mutable state. In some cases, what we would do is the failure would be handled on a separate thread, but if we pass the objects to that other thread, there's this little bit of mutable state that says, hey, you're part of this transaction on this thread. You pass the data over to that other thread, and all of a sudden, all hell breaks loose, unless you pass the transaction along as well, right? All sorts of craziness that we didn't know when we first stepped into it and just showed up during the refactoring, right? All that hidden complexity. So there's a pattern to deal with this in effective Java, and the pattern is prefer immutability. When did effective Java come out?
That was like 15 years ago, maybe?
15 years ago? Yeah, so even then, back then, we're starting to push immutability. And it didn't really take on as much as it could, and partly, we're going to walk into that, it's a little bit hard today. Guava immutable collections are a good example of where immutability can be a good pattern. You try to make use of what's called structural sharing. So one of the issues with immutability that people kind of throw at it is performance. I'm copying all this data. Well, actually, you're not. And if you are, you probably aren't implementing your immutable collections efficiently. What you really want to do is when you make a change to an immutable object, you can make use of as much of the underlying original object as possible. So you want to design collections that allow you to do this, allow you to reuse the rest of the underlying collection. And so you're only making small diff changes, and the relative efficiency and performance should remain the same. So yeah, our new paradigm is immutable by default. This is where the language itself makes it easy to be immutable. And pure functions, as James was showing with that add one, where effectively you take in values and you can only produce a result from that value that you took in. You can't touch other things.
Yep, and a pure function given a specific input should never produce a different output, is how we look at pure functions.
Yeah, that's known as referential transparency. If I have the same reference, like add 1 of 2, I should always get the same value no matter where that is.
Okay, so that's great. We want to move towards a world of immutability by default, but it turns out that it's a little bit hard. And so let's walk through some examples here and see what the world can look like. So we're going to start with our builders. So vehicle builders, what I have here is a way of constructing immutable objects. And we're going to walk through this sample. I've got a vehicle which has a name, a number of wheels, and has maybe a number of cylinders to it. And then we have some default values. So if I want to construct my vehicles, and I want to handle these optional these default parameters, I need to now create a whole bunch of different constructors. And the number of constructors just grows and grows and grows to be able to handle all the different cases for how I want to assemble my immutable vehicle object. And we have some getters there. So a pattern emerged in Java and other places, which is a builder. And the builder says, all right, instead of doing all those different constructors, what you can do is do a mutable builder and then call .build, which will create our immutable value object or whatever the object that we're building is. And so this is an example of our vehicle builder where we've got our defaults and then we've just got a few small methods to update, overwrite values. So that's doing mutation, but then we can call .build, which is going to return our immutable object. So this became a very common pattern in the world of Java for building these immutable objects, which is great. It's helping move us towards immutability, but the syntax was still pretty verbose for being able to construct these. We still did have the builders with the mutation, and I've run into a lot of problems with builders where you don't call the right thing, and so then you get an unexpected null somewhere, and so on and so forth. So let's take this example a little bit further, where we're going to use our vehicle builder. We're going to assemble a Pinto, a Tesla, and a Ferrari, and then that's great. We get our immutable vehicles, and now we've got a new object, an owner, which we can see down here. Our owner is, again, an immutable object. It's got its builder. It's got its constructor there. But now we need to take our builder and we're going to set our owner builder. We're going to set the age of the owner. We're going to add our vehicles to it and we're going to build it so we get back our owner. But now let's say we want to mutate one of the vehicles inside of this owner. Things get a little bit tricky in the immutable world. So we're going to go to our vehicles. We're going to find our Tesla in our list of vehicles. We're then going to update our Tesla, but to update our Tesla, we have to go back to a builder so that we can do our mutation. And then we're going to set our number of cylinders on our Tesla to 8. I have no idea why we want 8 cylinders on our Tesla, but we do. And so then we call .build to rebuild this into a new immutable object. But then ultimately we want to update that Tesla in the owner. So we have to get our list of vehicles that are not a Tesla. And then we need to take our owner, turn it back into a builder, clear out our vehicles, add all our vehicles that are not Teslas, add our updated Tesla, and then rebuild that thing. All just to be able to mutate a property on some object within that thing. And so, it's great that we're dealing with a lot of immutable objects here, but there definitely was a lot of programming overhead to be able to do what we wanted to do. So let's take a look at an example in Scala. We're going to be hopping around between a bunch of different programming languages here today. But I want to point out that this pattern of having immutable objects and being able to have defaults and those sorts of things has become something we've seen in a number of different programming languages. So in Scala, there's something called a case class where we can construct our object. We can give it defaults like the number of wheels, defaults to 4, and then we can construct our vehicles. You can see I can create a vehicle without those parameters. I can specify the parameters, or I can also name my parameters as another way to construct my objects. So really nice declarative syntax for being able to construct instances of objects. And then if we want to make a change to something within that, Scala has the ability to have a .copy method, and then we can use name parameters to set the parameters on that, and that gives us back a new immutable instance.
A three-wheeled Cadillac, man.
A three-wheeled Cadillac, my favorite kind.
Yeah.
So, so a lot nicer, more declarative looking syntax for being able to construct our immutable objects. But we still have that problem of when we've got this giant tree of objects and we want to do some mutation down in the depths of that thing, how do we do that? And so we wanted to show you another pattern that is emerging for how to deal with that particular problem. And Josh, you wrote this lenses code, so I'll let you walk through this one.
Yeah. Okay, so this pattern, effectively what we're trying to do is we're trying to treat the object graph in your programming language kind of the same way we would like a graph database. And we're trying to create queries against that object graph that can manipulate and work on the graph itself, right? So in this case, we're actually constructing queries. So vehicles here is a value that will take an owner and extract all of the vehicles within that owner, okay? The syntax, gonna apologize if you're not familiar with Scala. We'll just talk through kind of what this does. The Tesla filter, what this is doing is it will take any vehicle and check whether its name is Tesla and then return it, right? So it's like a filter in a query, like a where statement. Num cylinders will take any vehicle and give me the number of cylinders. Now, one thing to note, the number of cylinders is a maybe, it's an optional. So that actually returns an optional int, not an actual int. Okay, so these are lenses or queries into my graph. And then I can construct a query, ignore the actual operators because they are confusing as hell. But I can tell you what they mean if you really want. The idea though is I grab all the vehicles off of an owner. For every single vehicle, I run my Tesla filter and then I grab the number of cylinders for that Tesla filter. So this will grab every single Tesla within a particular owner and give me the number of cylinders. And now I'm going to take my query and I'm going to turn it into a mutation against owners. So the owner wants to install a V8 on a Tesla for some reason. So I take that query, optional cylinders of Tesla, and I set it to be 8. It's sum 8 because I'm working against optionals, which are Scala's, attempt to get rid of null. So you have sum and none instead of null and values. And then I can put raw integers and yay. Okay, so then let's make use of this program. I construct an owner, which is a rich guy, age 43. He has a Cadillac and a Tesla. And then I'm going to install this V8 on my Tesla. So I call that function that I just computed, and it should take the owner and immediately give me a new Tesla.
Great.
Do you want to run that?
Yeah, let's run this thing and
Okay.
see it actually work. So we did see our constructors from above, but the one that we want to show was here's our original owner. You'll see that the Tesla doesn't have any cylinders. And then after the lens has gone down into our vehicles, found the Tesla, and then modified that to give it 8 cylinders. So this is using the lens pattern as a way to do mutation, deep mutation on a graph of objects using a query, and then give us back a new immutable instance of that thing.
So you might already be familiar with, say, .NET and LINQ as a means of taking OO style code and encoding database queries into your language. This is kind of even further, right? We're actually encoding graph queries into our language against our own object graphs. And so this is something that's starting to get really teased out and really, I know in the Scala ecosystem, it's showing up a lot for JSON parsing and JSON libraries and manipulating of JSON because it's very graphical. And we're starting to see that kind of work its way further down. It's a little bit further out than some of the other patterns we're showing, but definitely expect to see things show up near you in a language that you prefer.
Yeah. Okay, so let's talk about another way to construct objects, which is using what's called combinators. So I'm going to use my vehicle builder to create my 3 vehicles, and then I'm going to create what's called a predicate. And a predicate has combinators to take our little bits of predicates. So this is a predicate is a function that takes, in our case, an integer and then returns a Boolean. And so I'm first have a predicate for balanced. So is this thing even? Because we don't want 3 cylinders. It would be unbalanced to have 3 cylinders or 5 cylinders or whatever. And then we have another predicate, beefy, which says if we have more than 8 cylinders, then it's considered beefy. So we can use these predicates in Java. So what I can do is I can go to a vehicle, get its number of cylinders, call filter. Filter takes a predicate, so I can give it one of those predicates. But here's where we get into the combinators, is that we can take those little bits, those little predicates, and assemble them together, chain them together. So I can call balanced.or, and or takes another predicate. And what I get out of that is another predicate, which is the balanced or beefy. And then I can use that predicate in the same way. So this is just another way to construct objects, construct immutable objects that are chained together in some particular way. And we actually, in the Scala example, actually saw this was actually using combinators, and we'll talk more about combinators and see them in more examples later. Okay, so that's all about constructing immutable objects and dealing with them. Josh, you want to give us a recap on constructors, lenses, and combinators?
Yeah, so effectively, languages are starting to add constructs to make immutability easier and more powerful, like in general, so that it becomes like the easiest way to write code. So optional defaults named parameters are really, 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 really important. Next, lenses are kind of starting to show up, and you're starting to see lens-like things kind of push their way down. So I think paying attention to that space is going to be important. Might not be applicable today, but it's coming. Dot copy in Scala is kind of your raw example of just, I can take a particular thing and change out one instance in it. You're starting to see that in other languages. So, macros in Scala allow you to do the crazy lens thing. But the dot copy operator actually showing up in Dart in a code generator for what's known as a built value. So in Dart, you have immutable values, you have built values, which are like, I can define an immutable value that gets a code generated builder, and I have a dot update method. The dot update method is almost exactly like the copy method in Scala, where I can take an existing object, I get a builder for it, and I mutate a few things and get back a new immutable object hidden within that dot update call. So you're starting to see this show up. Combinators are a awesome construction model for taking little pieces of immutable objects and making a bigger, more complicated one in a way that maybe you don't have to regenerate the entire structure to change a little piece. So in Java, we had predicates, right? That was our example there. There's other places where this shows up. Kotlin DSLs, a lot of these are combinator based. You do little things and join them together. In Scala, you have parser combinators, serialization libraries, pretty much almost everything that I work with. And then actually a lot of these reactive APIs, like reactive Java, they actually are composing little reactors, right? So you make a reactor, you compose it with another one. That's a very combinator-like API of taking small concepts and joining them together.
Great, so we've learned about constructing objects and dealing with mutations in the immutable world. But now let's talk about how we deal with some other challenges. So we, in the Java world, we needed to have a way to have some data representations and then separate out our data representation from the logic that gets performed on these data structures. And so we came up with another silly example where we have the style object, and our style can be a tab, a space, an identifier, or a code block which contains other styles. And then we're using the visitor pattern, which emerged as a way to separate out our data representation from the operations on that data. And so we have our style visitor, which knows how to take a tab, a space, an identifier, and a code block and do something with it. So then we need to actually have an implementation of our visitor. So we've got our a style code visitor, which returns for a tab, of course, the right thing, 2 spaces, and returns 1 space for a space, returns an identifier, but then can also recursively deal with a code block, which has that list of styles. And then we've also got a horrible one. Okay, so pretty typical in the Java world, these visitor patterns, but a whole lot of code here just to separate out this our data from the actions that we want to perform on that data. So let's run this thing so you can see what our fun little program here does, and I don't think I need a breakpoint. So I give it something like an abstract syntax tree with a tab, an identifier, space, a tab, and then another identifier, and our nice visitor formats that very nicely, and then our horrible formatter prints some emoji for some reason.
Did the tabs become
for
emojis?
tabs.
Is
the
that
tabs
what
become, that's what tabs should become. It's just some emojis, you know.
Yeah.
Okay, so in Java, this was our way to have our data representation separate from our implementation. A lot of kind of rigmarole to be able to do this. So let's look at an example where we can do this a little bit differently. And so I'm going to be using Kotlin. And first I need to go through a couple of kind of foundational pieces for this, and then we'll put it all together. So there's something called algebraic data types. Algebraic data types are the ability to combine different data types in 2 different ways primarily. So imagine that I have 3 types, an A, B, and a C. And for my simple uses today, these are all just Booleans. So I create my instances A, B, and C, and we're going to look at 2 different ways to combine these different values together. The first way is what is called a product type. And a product type allows us to AND together different types. In Kotlin, there's out of the box support for a product type in what's called a pair. And so with a pair, we can give it a pair of values. In this case, I'm giving it an A and a B. And then we can also construct something with 3 values using a triple. There's other languages use what are called tuples to handle this same sort of thing. So this is ANDing together multiple types. Now, the reason why this is called a product type is that if we think about the number of values that this first pair can have, it can have 2 different values here, and it can have 2 different values here. The triple, 2, 2, and 2. So what we do is we multiply together those 2 and 2 in the case of Booleans, because that's what our types are. And in the case of the triple, 2 times 2 times 2 gives us the total number of possible values that we can have. And so because this is multiplication, this is a product type. So that's the product types in Kotlin. We can also say these are ANDs, we're ANDing together these types, or we could call it an intersection. There's another algebraic data type that is called a sum type. And a sum type can be either one type or another, or multiple versions of that. So in Kotlin, there isn't an out-of-the-box type to represent a sum type, but you can create your own using a sealed class. And so I have an either that has a left and a right, and those are type generic on an ln and r. And you'll see that a left has a property left and a right has a property right. So now I can construct an either left or an either right and give it my property. What I get out of this is an either of A or B. And then if I want to, I can construct a trither type, which has a left, middle, and right. And then I can construct my trither, which could have 3 possible values. And so the reason why this is called a sum type is that if you consider the possible number of values that this one can have, it's 2 plus 2, and it's plus instead of sum, or instead of multiplication. And then the trither can have 2 plus 2 plus 2, so 6 possible values can be in this trither of ABC. And so that's our sum type, and you could call it or a union as well.
So one thing I want to add here is that either type, you've probably seen it before, but it hasn't been called either. It's probably been called result, where the result can either be a success or a failure. And so you get some sort of failure type, which is usually locked down, or you get a result of like the value you were looking for. And so either is actually used a lot in modern APIs, just not called that.
Sum, you see it as try, you see it as, what other examples of a sum type? We see them all over the place now.
Yep.
Okay, so that's our foundational algebraic data types. And now let's actually do something useful with it. So to do something useful with algebraic data types, you kind of need pattern matching. So pattern matching is the ability to take in something that is a sum type in this case, and then have logic that depends on what it actually is. And so I'm using my either left, creating an L, using my either right, creating an R, and now I can pattern match on this thing and say, all right, when we have an L that is an either left, then Kotlin will smart cast that to an actual either left. And so then we can call dot left on this. We can't call dot right on it because it is smart cast to an either left, and either left doesn't have a property named right on it. And then we can pattern match on the either right as well. But one of the nice things about using sum types is that the compiler knows all the possible sum types that exist for a given type. And so if we comment out this either right, then Kotlin is actually going to tell us, hey, you didn't actually match on all the possible patterns for this thing. And I think in Kotlin, maybe it's just a compile warning. In Scala, you can turn it into a compile error. But now let's actually do something useful with this. Let's take our program that we had earlier in our visitor pattern where we had separated out our data types. These are our data types. We have a data class, which is Kotlin's way of, another way of doing a product type in Kotlin. And so we have an identifier, in this case only one value, and then we have our block, which is our list of parts. And so now we've defined our data types, and then we can use pattern matching to actually do our parsing, and we can even recurse on this function as well to do handle our block. And so this is now a function that all it does is take a part and returns a string, but now knows how to operate on those different part types using pattern matching.
So that's 12 lines of code. How many lines of code was the visitor pattern?
It was a lot. It was a lot of code. We did have another style. We did have another style.
Oh, that's true. That's true. Okay, so about 109. But you can see the differential. Like this makes visitation and ADTs viable.
Yep. Okay, so that's ADTs. Josh, you want to do a little recap on that?
Sure. So the idea here is we're trying to actually decouple the behavior from the data, right? So like we want to construct our data and we need the behavior to kind of be external. If you think about this a little bit, you know, a lot of my microservices are taking in data, performing behavior on it. The data might be in a format I can't control. And so decoupling that actually helps a bit. Pattern matching is the magic that makes it work. It's come into Java. It actually looks really nice in Java. The spec, I really like it, surprisingly. The Scala types and extractors is an example if you want to see kind of the power of what pattern matching is. Scala seems to be the roadmap for things that come into Java. The Java spec actually matches Scala's pattern matching very, very directly. There's almost one-to-one correlation for different components. So I definitely recommend looking at it. Kotlin types with SmartCast is pretty good. It gives you about 80% of what you want from pattern matching, and it's missing a little bit extra that will be coming to Java.
Okay. So we've got our ADTs and our pattern matching. Let's go on to the next method that we're going to talk about, the next thing that's changing, which is what might be called ad hoc polymorphism. But let me explain what the concept behind this is. Let's say that we had a list of characters and we wanted to have a sum method. For some reason, we wanted to have a sum method on this list of characters. So if we have a list with an A and an A, then the sum of those would be a B. If we have a list with an A, B, and C, and we sum those, then we would get what is it, the sixth letter of the alphabet, or something like that.
I bet you could run it and find out.
That's where we can run it and find out. Okay, so in traditional OO, the way that we would do this is through inheritance. We would have some extension to our iterable of char that would add the sum method. but there's some new patterns emerging for how to do this. And what we can do in Kotlin is we can add an extension method to our iterable of char that's sum, and then knows how to take our characters and do the summing on those characters. Okay, so we can add that extension method so that we don't have to create a new class. We don't have to use inheritance. We can just add this method to anywhere where there's an iterable of char. We could do the same thing with an iterable of string. So we can add our sum method to our iterable of string there. But let's say that we wanted to be able to add the sum method to more than just iterable of string and iterable of char, but iterable of anything, iterable of t. Well, the way that we would do that is we would have an extension method, and I called it sumT, that takes a thing that knows how to convert to a char. So it knows how to convert t to a char. And then we would write the implementations, in our case, the string and char methods that know how to do that conversion. Okay, so now we have, for an iterable of t, we've got our sumT method, and now we can call that thing on our list of char or our list of string, and we provide it the converter that it needs to be able to do that. But things get a little bit trickier when we want to be able to call sumT on something that contains a list of char, or list of a list of a string. In that case, what we need to do is be able to have a converter that knows how to take an iterable of t. And then we need to then use a different converter within that to then convert that t to the char that then we can sum. And so if we wanted to do this in Kotlin, we can add that extension method, but then we do need to explicitly give it this chain of those converters so that it knows how to walk through the whole tree to be able to do all that conversion. And so you have to explicitly give those methods. And so things get a little bit unwieldy as our type tree starts to grow. Okay, so we've seen some ad hoc polymorphism, but I want to switch over to Rust, which is a language that has support for making this quite a bit nicer.
Yeah, so you saw that sum method was far more flexible, right? The downside is it just started to become unwieldy. Anyway, go ahead, James. Sorry.
Yeah, you could explain the Rust code since you wrote this one.
Oh, okay. Yeah. So we're going to do the same thing where we define a trait, and the trait is kind of like classes in Rust, but not really. So this is, I define a interface that has a method where I know how to take a particular type and turn it into a character. And then I'm going to define an implementation of that for character. I'm going to define an implementation for string. And that's just the Rust syntax there. And then here's an interesting one. I define if I have a type that already has a toChar, I can define an implementation of toChar for a vector. And you'll notice that James and I pronounce care differently. I apologize. It's the only hiccup in our friendship. Anyway, then I can define the sum method, and the sum method, you see this colon operator. It's like I implicitly take in the toChar interface for type T. Like compiler, go figure that out for me. And then I'm going to take in a vector of t, and I'm going to do that same operation. And this is just the Rust equivalent. But then you can see in where we make use of it in the main method, we're not actually providing that extra parameter the way sumT was in Kotlin. The compiler is doing it for us. It is automatically detecting it. And so if we actually change, yeah, we should run it first.
Let's go run it, yeah. Okay, so we'll go do cargo run. And so this will run what we have, and we'll see a plus a equals c. I thought that was supposed to equal b. I think you got a bug in here.
Oh no, it's a plus b. Look at the code.
Oh yeah, that's right. In our description,
we didn't reset it after we did the walkthrough.
That's right.
When we did our practice walkthrough. Sorry, we made it a plus b by accident. Okay.
Okay, so
anyway.
That all worked. That's great. It found the implementation that it needed to do that conversion. But if we go and convert this instead from chars to integers, and then we try to run this thing again, then you'll see that I get a really nice compiler that says, hey, I don't have a toChar that knows how to handle an integer. Here's all the implementations that I have, and there is not one for an integer. Okay, so this is called a type class, and the ability for this compiler to figure out and fill in those things that are needed is a type class. And so let's do a little wrap up on extension methods and type classes.
Yeah, so effectively we're looking at a different way of adding functionality to existing types without having to use inheritance, right? Like we've found some limitations with when and how inheritance can benefit us, and we'd like to add behavior without that and without the kind of negatives of inheritance. Type classes allow us to kind of make extension methods with a cleaner syntax, but more importantly, we can define methods that work against interfaces in a very, very generic way. And then the person who gives you the piece of data can define an interface for a class they don't own, where they didn't write the code for it. This is known, some people call it type-safe duck typing, where I can define, here's what a duck looks like, here's the interface for it, and you can pass me anything as long as I can infer that interface. Java has aspect-oriented programming where they kind of like do this ad hoc with reflection and stuff. Like, hey, if this method has the word, query, we're gonna like throw transactions around it. But Kotlin has extension methods and only extension methods to kind of add behavior to existing things. Scala has implicits, which do extension methods and type class derivation and all sorts of craziness. Rust has traits, which is a smaller, cleaner implementation of this that works just with those trait and impls and kind of does the work for you. So C++ actually had this for a long time with partial template specialization, where you can actually define a templatized class and defaults that kind of get looked up. So you kind of see that in C++ in a very ugly way, and they're kind of trying to make it nicer with concepts. But if you look at how C++ standard template library deals with like memory access and types of that nature, you'll see a lot of these type traits in almost all of the standard vectors, standard whatever classes.
What about
someone asked about extension methods as mixins in the chat. James, you're muted. I don't know why you're muted.
my kids are yelling in the background, of course, so.
Oh, okay.
Okay, yeah, mixins. How does this relate to mixins?
Yeah, so mixins are a way of adding into a class, right? And you can add in new methods to a class, but can you do it to a class you don't own? Like that's the real big thing to type classes, traits, and extension methods that is kind of a real powerful feature, is I can take a class that I didn't write and I can add something to it, right?
And then what about
that's the important bit.
Does .NET have anything like this?
I believe .NET has extension methods. I don't remember what the status of type traits are in .NET. I apologize. And I know it has extension methods, and I know that you do the extension method thing with it.
Okay, and then Go?
Oh yeah, Go, actually interfaces in Go are very, very similar to the type classes and traits, right? You define an interface that you define your method on, and then when you have a structure, if you have those methods, it'll automatically fill out that interface with the methods to allow you to kind of, call that more abstract method that only works on an interface.
Cool. Okay. So let's start to pull together a bunch of these different concepts. And so we're going to look at an example of JSON serialization or deserialization in Scala. And so first, we're going to use combinators to create a validator for JSON parsing. So I'm going to say, all right, if I am parsing a string, then I can use a combinator to make sure that the first letter is uppercase. So now I have a validator here, but then I can combine these validators together using combinators. So I've got a minimum length of 2 validator, and I'm going to combine that with, it starts with an uppercase. And then I'm going to use combinators to combine all this stuff together to do my JSON parsing. So I'm going to say, all right, for the name property, read a string, run it through the name validator, combine that with a numWheels reader, which is going to read an int, and then a numCylinders, which is going to read a nullable int, and I'm using that vehicle. Okay, so I've got my JSON string. This is just a string, and I want to be able to parse that JSON. And you'll see that my JSON reads doesn't get actually explicitly used anywhere. But you'll see in IntelliJ when I double click on it, it's telling me, hey, that actually is a parameter to this validate method. And I could actually come in and specify it explicitly, but we're using type classes. And so we don't need to specify that. It'll just get pulled in by the compiler. Okay, so my first JSON block is just a lowercase single v. What we get out of validate is a sum type result, which is either a success or a failure, and we're gonna print out the result or the errors. So let's run this thing so we can see what this looks like using combinators, type classes, and sum types here. You'll see when I first run it, the validator is giving me both errors. If we come in and just add an uppercase letter to pass one of the validators and rerun it, then we should see just one validation error. And if we come in and pass both, then we will see, I've spelled bubble wrong, but that's okay. Then we will see the actual result, which is our vehicle, which has been parsed from JSON and has the properties there. So serialization ends up being one of the places where a lot of this stuff all comes together using type classes and sum types and combinators and all the pieces that we've been learning about. Okay, let's talk a little bit more about serialization, since now in our future of OO, where we're much more service oriented, we have to deal with serialization in a lot of different ways. So Josh, run us through serialization.
Sure. We've tried to solve serialization a lot of different ways. So Corba, SOAP, JSON, Protos, you know, Thrift, that sort of thing. This is the serialization format is the serialization format of like networks. And, you know, we've gone through like code gen or just like dealing with the raw structure itself. And then we also have a different kind of serialization problem of like sending things onto disk. And we've tried like Java serialization, Cryo, Avro, Parquet, where we kind of read from the language and try to figure out how to put it onto disk or into the network. But going to and from objects is hard. There's a bunch of reasons, right? Data types are not universal. We don't use the same data everywhere. The objects can change over time. We might want to put behavior on those objects. We have different programs we need to pass things between that have different launch development life cycles. The efficiency can vary greatly between how you put it on disk. Maybe I need to worry more about CPU. Maybe I need to worry about network bandwidth. It depends, right? It's not always the same. So there's two kind of macro approaches. We either have converters, where we take a object in a language and we convert it into a serializable form and pass it off, or we have generators, where we take a definition that's external to my language and generate code from it, right? Those are kind of the two approaches for serialization. Converters, you can see they aren't cross-language, right? And that you often kind of use reflection to read into things. And so if I refactor a bit of code to solve a bug, I might accidentally create a new serialization format. The generator approach, one of the reasons we've been covering a lot of these type classes and ad hoc polymorphism is because generators live outside your normal tooling. The code that's generated is not flexible, and you find yourself wanting methods on these things, right? Wanting to create behavior on these auto-generated data libraries. And so we kind of showed you a little bit how to deal with that. We think type class derivation is the future. I have a prototype in Scala 3 just to show off some of what can happen. And I think this is going to hit other places, specifically like Rust, Haskell, that kind of stuff. The idea here, though, is you can derive a type class from your case class. So here we have this derived syntax. This is new in Scala 3, where you define a structure, and if I have supporting serializers for ints, strings, and arrays of things, it will actually derive the implementation of serialization for me, right? Not only that, at compile time. Not only that, we actually have in this particular library bidirectional support with protocol buffers, where we can create a Scala class that actually maps directly to a .proto file. And you can serialize back and forth between the two. And so you could think of a new world where you define things in your language and it generates this .proto file that then is usable, or you know, you could insert Thrift or whatever serialization format you're using. Where I'm Google, so Protos. You can imagine that world where it kind of generates that. So you kind of get a little bit of the best of both worlds, you know. Or I start using type classes and derivation to kind of take these generated proto files and add in the methods I need automatically.
Okay, moving on because we are running out of time. We wanted to kind of try to pull together some of these ideas into a actual like microservice-y example. And so what we have is we've got a microservice that returns a random number. We've got a microservice that returns a random word. And what we want to do is call our random number microservice, and then for that many times call our random word microservice and assemble a sentence together. So we started with Spring Boot, and we used the REST template, which is using just a blocking HTTP example. And we then are able to make the calls to our REST services. And then what we do is very simple. When we get a GET request to /, then we're going to get our random number. We're going to make those calls to our random word service, assemble our words or words together into a sentence, and then join them with spaces and return it. So that's our very basic example here. And let's go take a look at, I've got this running up on Google Cloud using something called Cloud Run for Anthos, but just a way to run this thing in Kubernetes. And so let's actually, what I really want to show you is I'm going to run a load test on this particular service. So I'm doing 2 threads, 100 concurrent connections, and calling this service, and we'll see how many requests we get through this. This is all blocking IO, and I get a 57 requests per second. I'll show you the actual service. There's my random sentence, basically.
That's a great sentence.
So pretty straightforward, but let me switch over to the reactor-based version of this example. We are going to be non-blocking. We're using RxJava, so we're dealing with monos, which allow us to make a non-blocking request. So I've got my non-blocking request for random number and random word, and then what I'm going to do is take my random number and then go do my fetches for my random words. I'm going to zip them all together. So this is using combinators and a bunch of other stuff we've been learning about, and then ultimately create our sentence and return it. So this is pulling together a lot of the different pieces that we've seen already, and then doing this all in a non-blocking reactive way. So let's go run our quick load test against our reactor-based version. And what we're hoping to see is this thing should be faster because we're able to take care. We're able to use concurrency. We're able to go across multiple cores, make multiple requests at the same time, which is all good stuff, all supported by a nice programming model that is using those combinators and other things that we've seen. Okay, it's a lot faster. That's good. That's exactly what we'd hope to see. But the syntax is a little bit weird in places for how we actually do some of these operations and how we make our concurrent requests and some of that, and how we assemble the results and that sort of thing. So we put together a Scala example, which we'll end with, where we are able to use combinators to assemble our GET request to get our number, map it to an integer, then create all of our concurrent requests to the random word service, sequence those together using futures. Future is a sum type that can succeed or fail, and then we get our words back and return those. So just to show you the end of this, I don't totally know why the play one is faster than the reactor-based one, but I'll run it just to show you. There is some fancy thread stuff that play is doing under the covers, which may be impacting this, but we will see that 10-second duration. That we get 457 requests per second, which is awesome. Okay, so that's our quick little example to try to pull together some of these different concepts into an actual microservice. And there's some concurrency pieces to this that are really interesting that we will wrap up with. So a lot of this is around demarcating splittable execution boundaries. And Josh, you want to handle this part?
Yeah, so the one thing about threads that we want to make sure we do is that we kind of tell the system when it's okay to allow another thread to run, and we want to make sure that we're not kind of blocking a CPU when something else could be running. So Combinators, composition of functions allow you to do this much better. You can make very clear, like the monos in the reactor Spring pattern or futures in Scala give you very clear, every single combinator is a splittable boundary. in the future, direct VM integrations coming. So instead of using like futures or coroutines or fibers, in the future, the VM will actually kind of treat blocking calls the way that play treats future boundaries. But for now, we're kind of using these promises, these futures, these reactors to kind of do the same thing and allow the VM to do a more efficient swap between threads.
And the Go runtime has that built in. Okay, we are out of time. Sorry we had to rush there at the end, but we will be in the Evolution of OO channel to chat with you after this. All the code for this is up on my GitHub there under OOP Evolution. So I hope that was useful. Thank you, Josh, and thank you all that attended.
All right. Thank you,
Thank
everyone.
you so much, guys. Sorry, it's just in the nick of time.
Just in the nick of time. Thank you.